All right, welcome back to class. Last class, we stopped by discussing how to balance half reactions. But I told you that in real sense, we do not have reactions in half reaction. They are actually in a combined reaction of both oxidation and reduction to form what we call a redox reaction. But before we can solve that, we first looked into half reactions before we can join them together and then balance the whole equation. So last class, I discussed this particular equation, which is arsenic oxide, moving from this point to this point, and we said each oxidation state is changing. So depending on what change in oxidation state we see, is what will tell us whether it's a reduction or an oxidation. Just for a recap, let's determine the oxidation state of the arsenide here. Arsenide here, we don't know the oxidation state, but we know there are two arsenides, so we can call that 2x plus oxygen. There are 3 oxygen, and when we know that oxygen always have a oxidation state on the normal circumstances of -2. So -2 times 3 in bracket to give us -6. All of this, which will be equal to 0. I said it should be equal to 0 because they are not carrying any charge. If this was to be an ionic compound, that is a compound carrying a charge, it would be equal to the charge. But here the charge is 0, so it's going to be 0. So 2x plus times minus is minus, that's 2x minus 6 is equal to 0. And as a result, it means that 2x would be equal to what? 6. When you take 6 minus 6 to the other side, comes 6. If I divide both sides by 2, I'll have x to be equal to what? 3. So it means that the oxidation state of our arsenic here is +3. So we will also do the same thing to find out what is the oxidation state of arsenic on the other hand. So to do that, we still have 2x. We have 2x plus, this time around, is going to be -2 times 5, which is -10. So let's just put -10 instead of plus -10 to still end up on that note. So if we take it to the other side, our 2x will be equals to 10. And then, of course, x would be equals to 5. X here would be equals to 5. So we have x equals 5. So having x equals 5 means that oxidation state is moving from what? +3 to +5. Is this oxidation or reduction? That's very correct. It is oxidation, because whenever oxidation number increases from 3, sorry, this is not 6, from 3 to 5, when oxidation number is increasing from 3 to 5, we say that is what? Oxidation. But in the real sense, what is happening here is that electrons are being lost. Arsenide is in +3 oxidation state, lose 2 electrons to come to the +5 oxidation state. So electrons are actually being lost, but the oxidation number is increasing. So do not forget all that. And from knowing that fact, we're able to bring out those. You can see oxidation state change from +3 to +5, which is oxidation. The difference in oxidation number is 2, of course, 5 minus 3. And so we know we'll add 2 electrons to the right-hand side of the equation. I told you don't have to memorize the right-hand side or left-hand side. We just use our common sense to know that since this is +3 and this is +5, and we know whenever we want to add electrons, electron means E minus. So if you add electron to anywhere, it is actually reducing the oxidation state, meaning that if this is 5 plus, where will I put minus that will make them come to the same value? It is definitely the higher one. If I put minus here, it will keep going down and going farther away from this. But if I subtract certain amount of electron from this, it will bring it down such that both of them will be on the same state. So how many electrons will I remove from this to make it this? Is 2. So I say +2E minus. If I put +2E minus on the right-hand side, the equation will be balanced. But this is a mistake here. This 4 here, I told you last class, it is supposed to be 2. So have that in mind. So now, today we shall look at a complete reaction. We shall solve maybe 3-4 examples. There are a lot of examples here that I would like you to lay your hands on. but I would discuss about 2 or 3 with you. Then we'll move on to the cell potentials and some other preliminary parts today, and then we conclude on it next class. Now, when half reactions of both oxidation and reduction reaction are written, a redox reaction can be balanced. So redox simply means reduction and oxidation reaction. So whenever we have the two reactions joined together, reduction reaction, oxidation reaction, then we call it a redox reaction. For example, this is a redox reaction because both oxidation and reduction are taking place at the same time. So let's see, where is oxidation taking place? Copper here is in what charge? 2 plus. Copper here is in what? 0. I told you whenever you see a free atom, the oxidation state will be what? 0. So it means from 2 to 0, is that oxidation or reduction? Reduction, because the oxidation state has reduced from +2 to 0. But what happened in the real sense is that electrons were gained. Is that okay? Electrons were gained, 2 electrons were gained, but the oxidation number reduces. I've explained the difference between these two. If you are still confused about that by now, please go back to the last class video and go over it again until you are comfortable with those statements. The oxidation number has increased, has reduced from 2 plus to 0, and that is enough to prove to us that it is reduction. But in the real sense, what has happened is that 2 electrons were gained, which removed these 2 electrons to make it 0. Automatically, if this is experiencing, if this to this is experiencing reduction, we can be rest assured that this to this would be experiencing oxidation. So it means we already know the other one will be oxidation, but let's also confirm it. This is sodium from 0 oxidation state moving to +1. You can see from 0 to +1 is an increase. Is that also in oxidation number? But what actually happened was that an electron was lost. So very good. Having said that, what do we do next is to break it into half equations. We balance the two half equations and then we join them together. So let's see. Let's start with the oxidation half. Oxidation half is sodium half, like we've said already. So the sodium half is moving from Na to Na+. So how do I balance this? Is I need to balance the electron. I told you where you have more electron is where you add electrons, because electron is carrying a negative sign, meaning that it will reduce the electron on the side you are adding electron to. And this electron here is how many electron more than this side? 1. So I add only 1 electron. So this is balanced. Now let's move to the next one. Reduction half Cu2 plus 2E minus to give me Cu. Now, how did I get this 2E minus? What I have here is just Cu2 plus to Cus. But in this case, there are the more electron is on the left-hand side. I add electron to where more electron is. So how many electrons more will I add? I'll add enough electron to make the oxidation state here the same with the oxidation state here. This one is 0. So to make this one 0, I add 2 electrons. So if I add 2 electrons, these two become balanced. Now, how do I join the two of them together? In order to join the two of them together, you cross multiply their number of electrons. How many electrons do I have here? 2. So I multiply this one by 2. How many electrons do I have here? 1. So I multiply this one by 1. But I don't need to show 1 because if I multiply something by 1, it remains the same. So I multiply this by 1. So if I do that now, this one will be multiplied by 2, meaning that I will be having 2Na, 2Na plus 2E minus. Is that okay? So it means that electrons on both sides is now balanced. This place now, if I multiply by 1, it remains the same. So this place, I have 2E minus. Here, I will also have 2E minus. By the time I multiply by these 2, I'm going to have 2 here, 2 here, and 2 here. By implication of that, if I add these two equations together, because 2E minus is on this side, 2E minus on the other side, meaning that they are on opposite side, it means they can cancel each other out. If they cancel each other out, I'll have this on the reaction side now, 2Cu2 plus 2Na to give me, these two have gone, so to give me my Cu, okay, plus 2Na plus. So this is the balanced reaction. This is the balanced reaction, and that's how you are expected to solve it. So this is another example. I'll solve this and then I'll pick one more example at random. There are other examples I would like you to sit down and then solve them on your own. So let me solve this. From here now, I have Fe2 plus aqueous moving from 2 plus to 3 plus. As this reduced or increased in oxidation number, it has increased in oxidation number. This is 2 plus and this is 3 plus. So it has increased by 1, so we call this oxidation. Automatically, we know this one will be what? Reduction. But we also have to prove, well, we also have to determine, what the oxidation state of manganese is here. Because our business here is with manganese. Our business here is with manganese and not the oxygen. This oxygen here is an extra atom, and don't forget, last class we already talked about how to balance oxygen. When there's excess oxygen, you add water to the other side of the equation, and then to balance the hydrogen in the water, you add a commensurate amount of hydrogen ion, H plus, to the other side. We've talked about that before, so I don't want to overbeat that matter. If you can't remember that, if it's difficult for you to understand what I'm saying now, you need to go back to the last video and go over it again. So what do we do here now is this already, we've already shown that from 2 plus to 3 plus is our oxidation half, so we bring it out. Oxidation half is Fe2 plus to give you Fe3 plus. I told you add electron to the side where there's more electron to balance it. So if I add electron, how many will I add? 1, because it is 1 excess. The difference between 3 and 2 is 1. So if I add 1 to this place, it makes this place become plus 2. So both of them become balanced. Okay. Now for the other one, which is our manganese, MnO4 minus plus Fe. Okay, now. So from here, what I have originally is MnO4 to Mn2 plus. Now I need to first determine what is the oxidation state of manganese. Let's do this on a plane. Let's do this on another plane sheet. All right, so this is what we are supposed to have in our reduction half. MnO4 minus to Mn2 plus. How do I know it's reduction? Let us determine the oxidation state of manganese on this end. So how do I determine it? I say manganese, I represent manganese with the X plus oxygen is minus 2 times 4, that's minus 8, minus 8, minus 8, and this will all be equal to what? This will all be equal to minus 1, not 0. Why? Because manganese oxide here is an ion, and you can see it's carrying a charge. Is that okay? And the charge is minus, meaning that it is minus 1. So that's what will be here. So this will be X now. This will be X minus 8, that's plus times minus, minus 8 is equals to minus 1. And of course, this will be X is equals to minus 8 going to the other side becomes plus 8. So I have minus 1 plus 8. Minus 1 plus 8, of course, that is equal to plus 7. Minus 1 plus 8 is equals to plus 7. So it means the oxidation state of manganese on this side is plus 7. So it's moving from plus 7 to plus 5. So it means the oxidation state I have here is plus 7. And here is to plus 2, sorry, from plus 7 to plus 2. So it means that how many electron more do I have here? 5. The difference is 5. So I add electron to where I have more electron. More electrons is here. I'm talking about more oxidation states, that is plus 7. So add electron to that end, that's plus. How many do they have in difference? 5. So that's plus 5E minus. Plus 5E minus will be added to the left hand side. Now that has balanced the charges, but that is not all, because there is oxygen here, whereas there is no oxygen here. So how do I balance that atom difference? I said whenever I want to balance oxygen, we balance it by adding water. So I add water to the other side. How many molecules of water do I need? Is the number of oxygen I need that will determine. So I need 4 molecules of water, so I can get 4 molecules of oxygen. So that will be 4. That will be 4. H2O. 4H2O is going to balance that oxygen. But by balancing the oxygen, that's created another problem of hydrogen. So how many hydrogens has it created? 8. So I balance the hydrogen by adding 8 hydrogen ion to the other side. 8 molecules of hydrogen ion, that is H plus. So 8 molecules of hydrogen ion. Now the equation balance. So this is the balanced equation for the reduction half. Having said that, it is now clear to us why we have 8H plus MnO4 minus plus 5E minus to give us Mn2 plus 4H2. That is why we have this equation. Now, how do we now balance this equation? To balance this equation now, I told you we cross multiply the number of ions, the number of electrons, sorry, we cross multiply the number of electrons. How many electrons do I have here? 5. How many do I have here? 1. That means I multiply this one through by 1 and I multiply this one through by 5. If I multiply through by 5, I'm going to be having 5 Fe plus 2 plus to give us 5 Fe3 plus 5 E minus. The purpose of doing this is so that the electrons can be the same, so that when I sum them together, 5 electrons are on this side, 5 electrons are on this side. I mean that both of them can cancel each other out. They will always cancel each other out. Then, of course, you sum up the rest. So what I have here now is 5 Fe2 plus 8H plus MnO4 minus. Then to give us Mn2 plus, which is this, plus 4H2O plus the last one here, which is 5Fe3 minus. I believe it is crystal clear, and the explanation I've given there is very, very clear to you. Okay, there are so many other examples that you can try out here. I want you to sit down with them, look at it clearly, just pick your pen, write out the questions, sit down and try it on your own. I'll also give you an assignment after this lecture to ensure you also solve and submit to me as I when requested. And you'll be expected to know how to do both the half reaction and the complete balanced equation like the one we just did now. So now electrode potential. Now we are here on electrode potential. So all that we have discussed so far are just the preliminaries that would help us to be able to understand and appreciate electrochemistry better. So I expect you by now that you can balance the redox reaction using that method there. And there's another method you can use to balance the redox reaction, but we'll stick to the method of half equation. It is most efficient. So just ensure that you understand that method very well. Now let's move on to what we call electrode potential. When a strip of metal M, known as an electrode, is placed in a solution of its aqueous solution Mn+, the following equilibrium is established. Now when we have a solution that is a solution of a metal Mn+, that means it is ionized, and then you have the metal dipped into that solution. That metal dipped into that solution is called an electrode. Now, it will give us this equation. The equation is Mn plus Ne minus, meaning that whatsoever charge is here is what will be in front of our electron, and that will end up giving us what? M solid. You can see our electron is on the left-hand side, meaning that this equation here for this is a reduction half reaction. This is a reduction half reaction. At equilibrium, there is a separation of charge between metal and ions in the solution. As a result, there is a potential difference between the metal and the solution. So because of separation of charge that will occur in the solution, there will arise what we call a potential difference between the metal, that is the electrode, and then the solution, which we call the electrolyte. Okay, the solution is the electrolyte, and the metal that is dipped into it is called the electrode. This potential difference is known as the electrode potential, and we represent it with E and then a circle on top of it. which means electrode potential. Is that okay? E with this round circle that is on top of it represents electrode potential. Now, electrode potential can be measured under 3 circumstances. Now, let's look at this. Let's consider this. What we have here now is an example of what was just explained. You can see this is our container carrying a solution Mn plus. In this case, it is +1. That's why I just plus. And then this is the metal, which is your M. Now, if in this case it was copper, if your metal was to be copper, then we're going to be having a Cu2 plus 2E minus to give us our copper, because of course I told you Mn plus Ne minus to give you M solid, and that's what has been used in this case. Now here we have our electrode. This is not electrode potential, is E0. Is that okay? This is the electrode of the cell. Now, so the electrode of the cell Cu2 plus to Cu, which is a reduction half reaction, is plus 0.34 volts. Don't worry, I will show you how we calculate this. Now, the positive value of E0, which is your electrode potential, indicates the equilibrium favors to the right position. Copper 2 ion, which is copper 2 plus, have a greater tendency to be reduced at copper electrode. So because the value is positive, it shows the equilibrium will favor the right, and what occurs on the right hand side is reduction. Okay, so it has a tendency to be reduced at the copper electrode. You understand this much clearer by the time we move on. So you can see now here we have zinc 2 plus Ze minus to give us zinc. In this case, you have what? Minus 0.76. The negative value of the electrode potential indicates the equilibrium favors the left position. So zinc ion, in this case 2 plus, have a greater tendency to be oxidized at the zinc electrode. So most likely this reaction is going to be occurring as an oxidation reaction on the left electrode, which is going to be our oxidation half. Okay, that is for metal. Now looking at non-metal. On the other hand, if looking at non-metal like chlorine, if we have chlorine gas, passed into this tube, and then you have a reaction that contains a chloride at 1.0 molarity. You'll be having your reaction this way. This is a F2 plus 2E minus to give you 2F minus. You have Cl2 plus 2E minus to give you 2Cl minus. Now you see both of them. You can see this one giving us a positive electrode potential, and this one also giving us a positive electrode potential. So positive value of the electrode potential of the chloride and that of the fluoride indicates the equilibrium favors the right, like we said before. Position fluorine and chlorine has a greater tendency to be reduced under platinum electrode. Don't forget, in this case, because we are talking about non-metals, the electrode is not going to be the same as the electrolyte solution, like we had copper in a copper solution or zinc in a zinc solution. In this case, we use what we call a platinum electrode. The more positive the value, the higher the tendency of non-metal to be reduced. The more positive the value, the higher the tendency for it to be reduced. In other words, fluoride is a stronger oxidizing agent than chlorine. Now, don't get confused that we are talking about reduction and yet we are saying fluoride is an oxidizing agent. Oxidizing agents get reduced. You've been taught this before in your secondary schools or in your knowledge of chemistry before now, that oxidizing agent, when we call something an oxidizing agent, it means that thing is going to be reduced in a chemical reaction. Anything that gets reduced is the oxidizing agent, and anything that gets oxidized is the reducing agent. So the greater the positive value of the electrode potential, the stronger the tendency for that metal to be reduced, the higher the tendency. So it means because fluorine is more positive, plus 2.87, it means it has a higher tendency to be reduced, and therefore it is a stronger oxidizing agent. mixture of aqueous ions. I told you there are three different scenarios. We've looked at two for metals, for non-metals. Now this is the third one, which is mixture of aqueous ions. Now, in this case, now this is your metal at 1 molarity, and then another mixture of another ion, another metal ion, which is also in 1 molarity. So this is mixture. This is not just a copper solution or a zinc solution or a chloride solution. This is a mixture of two different ions, both at 1.0 molarity. That's their concentration. Now, a potential difference also exists between ions in an aqueous solution. So if I have chromium, for instance, chromium 3 plus E minus will give me chromium 2 plus. Fe3 plus E minus will give me Fe2 plus. You can see both of them giving different electrode potential. Based on the electrode potential value, chromium 3 plus is more stable than chromium 2 plus, as equilibrium favors to backward reaction. It favors the backward reaction, which is electrode potential is negative. Whenever it's negative, it's favoring a backward reaction. And then based on the electrode potential value, Fe3 plus is less stable than Fe2 plus, as equilibrium favors the forward equation, which is electric potential is positive. So obviously, because it favors the forward, Fe2 plus will be more stable than Fe3 plus. That is, Fe3 plus is less stable. This is still the same statement either way. So having said the three different ways, now we can talk about standard electrode potentials. So we talked about electrode potential, but we also have what we refer to as a standard electrode potential. Now, by definition, the standard electrode potential E naught of any metal ion, that is E naught of any Mn plus / Mn of a metal M, is the potential difference between the metal and the aqueous solution of the metal ion of concentration of 1.0 mole per dm cube at standard temperature and pressure. Standard temperature is 25 degrees Celsius, which is the same thing as 298 Kelvin, and standard pressure is 1.0 atmosphere, ATM, measured relatively to the standard hydrogen electrode. So by definition, that's what we refer to as a standard electrode potential. It just refers to the potential difference between a metal and the aqueous solution of a metal that is at 1 mole per dm cube, that is 1 molarity, and at standard temperature and pressure, measured relatively to a standard hydrogen electrode. Standard hydrogen electrode is also known as the SHE. So that's what we call a standard electrode potential. So let's see what a standard hydrogen electrode is all about. It is impossible to measure the electrode potential for an incomplete half cell. It can only be measured for a complete circuit with 2 half cells. That is, only differences in electrode potentials are measurable. So the standard chosen for the electrode potential is a standard hydrogen electrode. So it's not possible for me to just measure just one cell. Like you can see all the diagrams that I showed you, all the three, whether a metal, a non-metal, or a mixture. I told you that each of those ones, they stood alone. They are either reduction reaction or oxidation reaction. So they must be measured against a standard. So the standard that we use most often is what we call a standard hydrogen electrode. There are other standards which we also see as we go ahead. So the standard electrode potential of other half cells are measured relative to the standard hydrogen electrode potential. By convention, the standard electrode potential for this reference hydrogen half cell is taken to be standard. So the value for this SHE is taken as a standard value. Every other one is measured against it. Is that okay? So what is the condition? The condition for this equation, which is this is our SHE equation. Make sure you know this equation, because I could ask you. This is the equation for the standard hydrogen electrode, 2H plus aqueous plus 2E minus to give us H2 gas. So what is the condition is that it must be at standard temperature, it is 25 degrees Celsius. I told you that before. That is the same thing as 298 Kelvin. And also the hydrogen must be at 1 atm pressure, which we have also stated before. And then the hydrogen the aqueous solution of the hydrogen must be in a 1 mole per dm cube concentration, which is what is here, 1 mole per dm cube. Otherwise, we can call it 1.0 molarity. Instead of saying mole per dm cube, we are still saying the same thing. Okay, so measuring standard electropotential of a metal or a metal aqueous solution. This is the setup of the apparatus to measure the standard potential electrode that E0. This is how we set up a standard measurement of it. We'll put our cell on the left-hand side. You can see here now, zinc, we measured it before, and we know that zinc usually have a positive value of standard electropotential, meaning that the reaction moves towards the right, and that is going to be talking about a reduction reaction. So for this now, you can see that's why we are putting it on this end. This is our electrode, the metal, which is zinc, and this is our electrolyte, which is the metal solution, which is your zinc 2+ in 1 molarity. And then we measure it against a standard hydrogen electrode, which is our SHE. This is just a standard. Now, this standard hydrogen electrode here has ATM, a pressure of 1 ATM, has a concentration of 1 molarity or mole per dm cube, and has a standard temperature of 298 Kelvin, otherwise known as 25 degrees Celsius. Now, in between the two of them is what we call a salt bridge. This salt bridge is made of saturated KCl and NaCl. It allows electrons to be exchanged between the two solutions. So electrons can move from this end to this end, and it also aids mobility. So that is the function of the salt bridge. So we have a salt bridge, and then of course attached to both electrodes is a potentiometer, which measures the electrode potential. So that is how the setup for every standard potential electrode is being set up. This is the setup. Okay. Now the chemical cell is set up by connecting standard zinc 2+ to zinc metal half cell to a standard SHE electrode. That is your standard hydrogen potential electrode. Now the EMF, which is the electromotive force for the cell, is 0.76 volts. We've showed this before. This is standard. You don't need to memorize this for now. I'll show you how to calculate them later, but this is a standard value given for zinc. The potentiometer points to the direction of H2 electrode in the external circuit, indicating electrons flow from the zinc 2+ to zinc, from the zinc 2+ zinc metal to the what H+ H2 gas half cell. So we could see that in the diagram that was there before. You can see the potentiometer pointing towards the hydrogen direction, showing the electron is actually moving from this part to this other part. So because of that, that's why the potentiometer is facing that direction. So we could see the half cell reaction for the zinc half cell. This is the zinc half cell reaction. The zinc solid moving to zinc 2+ plus 2E-, and then you can see your 2. You can see this one is going from 0 to 2+, which is oxidation, and then this one is going from plus to 0, which is reduction. So the overall reaction, just like we've been balancing before, these are the two half reactions. Then you balance it. This cancel this, such that you join the two of them together. Zinc solid plus 2H+ aqueous to give us H2 gas plus zinc 2+ aqueous. So the cell notation can be written as this. Now, this is very, very important to you. We call this a cell notation. Call this a cell notation. Now, this whole cell, I wouldn't ask you to draw this for me in an exam. At least not if your exam would be online. If it were to be a PPT exam now, I would be able to I'll be able to ask you to draw this, but for the sake of the type of exam you most likely write, I would ask you to provide a cell notation instead of that diagram. So how do we provide a cell notation? Now, if you see this diagram here, what is happening here is oxidation, moving from 0 to 2 plus. So we write the oxidation half on the left here, Zn solid. This straight line is used to divide the metal from the electrolyte. So the electrode stroke the electrolyte, which is Zn2 plus. This double line means the salt bridge. It signifies the salt bridge dividing both cells. Then this is how we write a standard hydrogen potential. H plus aqueous, comma, H2 gas, then you separate it with its own, what do we call it now? Its own metal. In this case, it is platinum. In the case of hydrogen, the metal that is used as the electrode in the standard electrode, hydrogen electrode, is a platinum. So you put your PT solid. You can see this place is oxidation and this place is reduction. You're moving from plus to 0. So you put it this way. This is how to write the standard hydrogen potential anytime, any day. So it is just this one that will be changing depending on what is the other half cell you are dealing with. So at the zinc electrode, electrons are donated, oxidation reaction occurs. I've said that. I'm going from 0 to 2 plus. At the platinum electrode, which is your standard hydrogen electrode, electrons are received, that is reduction occurs. Since zinc is oxidized in a standard hydrogen electrode, the standard EMF value is minus 0.76 volts. This value is a standard value. You don't need to memorize it. So let's see another one. This one is a silver aqueous solution, Ag plus. We'll be setting this one up also against a standard hydrogen electrode. You can see everything on this end is the same thing. It is the same standard hydrogen electrode. The only thing we've changed here is this half cell. Instead of zinc, now we're having silver electrode in a silver ion solution, electrolyte. So, of course, the concentration remains 1 mole per dm cube. So this is a silver half cell reaction. So, but in this case, you can see the potentiometer is pointing towards what? The potentiometer is pointing towards silver, meaning the electron is actually moving from here to here. So, will oxidation be occurring here in this case? Let's see. So, let's see. The chemical cell set up by the connecting a standard Ag plus to Ag0 half cell to a standard H plus to H2 electrode. The EMF in this case is positive 0.80 volts. The galvanometer points to the direction of silver, like I showed you in the external circuit, indicating electron flows from our hydrogen potential standard hydrogen electrode to your silver electrode. And of course, the half cell reaction in this case will show, instead of oxidation to occur in the silver, what will be occurring is reduction, because you can see that electron is actually flowing to the silver. And we know that in reduction, electron is gained. The one that gains electron is the one that gets reduced. So because of that, the silver is not being oxidized like we had in your zinc. The silver is going to be reduced from silver 2 plus to this. And in the case of the hydrogen, you can see I've turned the equation upside down. The previous equation, I had this H plus on this side because this one was actually being reduced in the last one, but here it is being oxidized, meaning that it is moving from 0 to plus. And of course, your 2E minus must be on this end to balance this equation. And of course, to balance the equation, you know I must multiply this side by 2, multiply the whole of this equation by 2, so that I have 2E minus here, I have 2 here, and I have 2 here. We've already done this already in previous classes. So this take care of this, and then I can sum up these two half equations to give us this overall chemical equation. So let's see the notation of this one. In the case of the notation of this one, is it silver that is oxidizing or hydrogen? Hydrogen, so it will be the one on the left. The previous one, you know, zinc was written on the left instead of hydrogen that we have here now. So it's because in this case, the value is positive, showing us that it's actually a, on the right hand side, what is occurring there is the reduction, and the oxidation is occurring in the SHE. So this is our SHE, standard way to write it. Your platinum solid become first in this case because it is undergoing a oxidation. So you put that here, put your salt bridge, which is this double line. I can ask you anytime, what does this double line indicate? It indicates the salt bridge, and then you put your other half equation there. At silver electrode, electrons are received, reduction occurs there. At the platinum electrode, donated electrons, so oxidation occur, and the silver is reduced in a standard hydrogen electrode. The standard value is plus 0.80. Again, do not memorize that. It's a standard value. I will supply it if I give you questions to solve. So now let's talk about the standard electrode potential of a gaseous substance. So we've talked about that of zinc solid in zinc electrolyte, that of silver solid is silver electrolyte. Now let's look at it for a gaseous substance. The chemical cell setup for connecting Cl2 Cl minus, of course, which is a gas, with a standard hydrogen electrode potential. Is what we have here. And note that the setup of the half cell reaction are the same for gaseous substance. So exactly the same. The only difference here now, of course, this remains the same. This is our standard hydrogen electrode, always on the left. And then on the right hand side, I have my my chloride electrode half cell, chlorine half cell. Now in this chlorine half cell now, I have my chlorine gas that is being passed into this electrolyte. Of course, you know this metal here now will be a different metal. This metal here will be platinum again. And then this is our Cl minus, which is our aqueous solution, which is the electrolyte here. So having that now, let's see what occurs. The EMF of the cell is 1.36. You can see that is a very positive EMF, and you can see it is pointing towards the direction of chlorine. So obviously, electron is traveling from our SHE to this chlorine half cell. So the implication of that is that what is occurring here is reduction, and what is occurring here is oxidation. So it will be just like that of our silver electrode. So that's exactly what will be occurring in this case. So in this case now, we can see that we have 1.36 volts, and the galvanometer points towards the platinum chloride. I told you we use a platinum electrode in our chlorine half cell because chlorine is a gas, so we have to use another metal as an electrode. So indicating electron flow from our hydrogen, standard hydrogen potential, our SHE, standard hydrogen electrode, sorry, to our chlorine half cell. So for the chlorine half cell, what will be occurring there would be reduction. So you can see this reduction moving from 0 oxidation state to -1 oxidation state. So it means it is reducing in oxidation state from 0 to -1, that's reduction. So what will be happening on this one there with the oxidation? You can see how it's the same way we had it in the silver electrode. And then the overall reaction, here we already have 2E minus, 2E minus, so there's no need to multiply anything, just divide both, take away the 2 electrons and sum both sides, sum the reactant side and sum the product side, and you have this overall reaction. So how do we write our notation? The same way, this is our SHE, which is going to be appearing on the left because, of course, this time also it is undergoing oxidation, and then the one undergoing reduction is on this end. Do not see, you can see here that we wrote it just the same way we wrote our standard hydrogen electrode, because this time around it is not a zinc solid in a zinc electrolyte, that is a zinc ion solution. But in this case, it is a gas. So we have to write the gas and then the solution, then we put our slash, and then we write the electrode. The electrode in this case is platinum solid. Okay, so at platinum electrode in the half cell of hydrogen, electrons are donated. Oxidation reaction occurs. Platinum electrode in the half cell of chlorine, electrons are received and reduction reaction occurs. And then the standard value is plus 1.36 volts. It's a standard value. Okay, we can also measure a standard electrode potential for a mixture of metal ions. It's possible for us to have a mixture of metal ion inside the same solution. So let's see that the electrode potential of a mixture of ion can be measured in a similar way using standard hydrogen electrode as the other half cell of the chemical cell. For example, in a mixture of ion 3 and ion 2, which is what we have here, you can see in this solution we have both ion 3 and ion 2. We are using a platinum electrode in this case too. We are not using a ion electrolyte, electrode. These are electrolyte solutions which contains both ion 2 and ion 3 in the same concentration of 1 molarity. You can see our potentiometer is pointing to the right, that is towards the ion Fe2 plus Fe3 plus half cell. So therefore, of course, what will be occurring here again is oxidation, and what's occurring here is reduction. So we can see all that clearly. Let's see the half cell. From the half cell here, you can see Fe3 plus E minus going to Fe2 plus. This is obviously a reduction, moving from 3 plus to 2 plus. And then the hydrogen half cell, of course, the same way we had it in the chloride and also in the silver, is the same way we have it here, undergoing oxidation. You can see the electrons are not balanced. We have 2 here, we have 1 here. So I multiply this one through by 2. So I have 2 here. That's why you can see 2 Fe and 2 Fe3 plus and 2 Fe2 plus here. But we multiply this one through by 2 and the 2 cancel 2. And that's why we have this overall reaction. I believe there's nobody confused on that again by now. If there's anybody, go back and watch the videos. The cell notation can also be represented the same way. We have it this way. Now, how do we represent this one? You also have your Fe3 plus, comma, your Fe2 plus, and then your platinum. I told you we are using platinum electrode. So the same information goes. Since the mixture is reduced by SHE, the value is plus 0.77 volts. Finally, for today, we have another standard electrode potential. Just like the standard hydrogen electrode, we call that one the Calomel electrode. All through till now, I've been using only standard hydrogen electrode as our reference that we are using to calculate for others. So, but we can also use another reference we call the Calomel electrode. Platinum electrode is known as the primary reference electrode. However, platinum electrode is a standard hydrogen electrode. But however, it is relatively difficult to set up and operate under standard conditions. It's very difficult for us to have a standard condition where we'll be having a perfect room temperature of 298 Kelvin and having 1 atm pressure with 1 mole per dm cube concentration. So it is more easier and safer to use what we call a Calomel electrode as our secondary electrode, that is our reference electrode. Calomel, what we have in our Calomel electrode is a mercury-based alloy. Calomel is a mercury-based alloy, and this is the diagram of our Calomel electrode. What we have inside here is a mercury. It's mercury metal, and that's what we use in our Calomel electrode. It can be used in replacement of the standard hydrogen electrode. And the reason is what I've stated. It is difficult to set up and operate the standard hydrogen electrode. So thank you very much for listening again in today's lecture. We shall pick it up from here. Next class, we'll look at factors affecting electrode potentials, and then we look at 1 or 2 other things, and then we'll round up our electrochemistry class. So please, I want you to pay very close attention to half cells, how to balance them, how to balance a complete cell, and then pay attention to the standard hydrogen electrode, how to write a cell notation, and how to know where reduction is occurring and where oxidation is occurring in the cell potential, and also know what your electropotential means. So thank you very much for listening. I'm going to send you questions to solve as assignment, but even aside that, there are many questions that were not solved in this class. So please lay your hands on them and solve them. So thank you very much.